Hey guys, this is Zal. This video describes how to do the last part of our recent assignment week 11. And it describes specifically Friday's part A, how to compute the various statistics that are used to diagnose the quality of our regression. Okay, so let's go over quickly what those two numbers are. The first figure that we looked at is, first of all, this is a regression of, here I'm working with the wage data set, okay? And what I did was I regressed wage on education. Okay, so the dependent variable is wage, the independent variable is education, and here I have my regression results. Okay, you'll notice that here are the ordinarily reported intercept and coefficients. But here we want to turn our attention to the three values that I have in bold: the R-squared value, the F statistic, and the p-value corresponding to our F statistic. Okay. Now, all three of these measures are measures of how well the data fits the line. You can see I have the data over here. Okay, here's the data. This is people's levels of education. Notice they're bunched up here on the X, and then wage is plotted on the vertical. Here's a line that I fit. Okay, and both of these measures over here are a measure of basically how far these points are away from the line. Okay. Now the R-squared value, people use this a lot. This goes from 0 to 1, with higher is better. And the most it can ever be, which would be 1, would correspond to all of the points in our data lying on the line, which is obviously not the case here. Okay. Now, this F statistic is actually a little bit more meaningful. Okay, so the F statistic, 111, you want to look not so much at the F statistic itself, but the p-value associated with that F statistic over here. Okay, this very small numbers, 9.3 times 10 to the negative 25th. Okay, now this number is a lot like the p-values associated with our coefficient estimates. Okay, and notice our coefficient estimate here has a very low p-value, and that low p-value indicates that the corresponding result, this 60.21 slope estimate that we're getting, is statistically significant. The lower your p-value is, okay, the greater the statistical significance. Okay, so this number here is very similar, except that if we were to have a lot of independent variables in this regression, each one of those would have its own p-value, right? But there would still only be one p-value for the F statistic. There would still only be one F statistic for the entire regression. So this number tells you about the statistical significance of our entire regression, our entire linear model fit. Okay, and the lower this number is, the better, the higher the statistical significance of the overall regression. Okay, so now having been said, how are these numbers computed? Okay, well, that's what our class on Friday walked you through. Okay, and I'm just gonna give you those instructions again in this video. Okay, so the first thing to understand is, the first thing we're gonna do is compute the things I have here. Okay, what I've done is I've copied over my regression coefficients, so you can see that these coefficients are just exactly what we have here. Okay, I've copied over my regression coefficients, and I'm using those to calculate the predicted wage. So what is the predicted wage? The predicted wage is the intercept plus the slope corresponding to education times the level of education. Okay, and what this value corresponds to is, it corresponds to the values on our regression line. Okay, so someone with 10 years of education, what is their predicted wage? Well, it's the value corresponding to 10 years of education on the regression line. Okay, now you can see that people's actual levels of wages, which are plotted in blue, do not necessarily equal the predicted wage. Some are higher than the predicted wage, some are lower than the predicted wage. Again, that's what we see over here, right? This guy, for example, we predict his wage is something like 870 based on his level of education, 12 years, but instead his wage is actually 769. Okay, so there's our predicted wage. Over here, the residual, okay, the number called the residual, is calculated as the difference between the wage and the predicted wage. It's, if you will, the distance that each point lies from the line. Okay, so now we're going to compute three numbers in rapid succession. The first number is the square. Okay, it's a sum of squares that we're about to compute here. So we're gonna compute a bunch of distances and we're gonna square them. The first number, okay, is each person's actual level of wage minus the mean wage of everyone in the data set. Okay. Now over here separately, I've computed the mean wage. This is the average wage of everyone in the data set. Okay. So this number here, okay, so this number is the true wage minus the mean wage squared. Okay. Each person's deviation from the mean wage squared. Okay, and compute that number all the way down for every data point. Okay. The second number here is the predicted wage minus the mean wage squared. Okay, so our predicted wage here, we just calculated that, minus the mean wage squared. The third number here is the residual that we just computed squared. Okay, so the residual squared. Okay, compute those numbers. You just computed those in rapid succession. What do those numbers mean? Well, let's go over here to our graph. Okay, so here, zoom in a little bit. Okay, I plotted the three things that we were looking at. Here is the regression line. Here in a red dotted line, I've plotted the mean wage of everybody in our data set. Okay, something like close to $1,000. Okay, and if we consider each point, okay, like for example, let's consider this point right here. Okay, this point right here. This person, okay, has a wage of $1,700. Okay, and notice that that is some amount of distance from the average wage of everyone in the sample. Okay, so this is the first number that we computed, the difference between the real wage and the average wage. Notice that that distance can be broken down into two components. First, the distance from this point, the real wage, to the regression line, that's the predicted wage. Okay, that's the second number that we computed. Okay, and finally, so that whole distance, okay, is equal to that distance, the distance up to the line, plus the distance from the line to the average wage of everyone in the sample. That is to say, the distance from the predicted wage to the wage of everybody in the sample. Okay, so we have this total distance, and it's broken down into those two components. Those are the three pieces that we just computed. Okay? Okay, so with those numbers in hand, I'm basically going to sum each of those columns. Okay, and that's what I've done in this table over here. The sum of squares total is the sum of this first column. The sum of squares in the regression is the sum of this column. And the sum of squares of the error is the sum of squares of the residual, is this final column over here. Okay? Now notice that these numbers are also reported when you do the actual regression itself. The actual regression itself here. Okay, you see the sum of squares for the regression, the residual, and the total. Okay, we have them in a slightly different order here, but total, regression, and the sum of squares of the error, that's also called the sum of squares of the residual. Okay, that's here. Okay. Now, immediately we can compute the r-squared value. The r-squared value is simply equal to the sum of squares of the regression divided by the sum of squares total. Okay, so this indicates essentially how much of the variation in our wage is explainable by the variation present in the regression line. Okay. So this number, like I said, computed is the sum of squares residual divided by the sum of squares total. This number can never be greater than 1. Okay, and in this case, it's something like 0.1. It's like 10%. That's a relatively low r-squared value, but it's not so bad. Like I said, this number really isn't quite as meaningful as the F statistic because there's no real guideline as to what is necessarily a very high or a very low r-squared. You can have a low r-squared value and still have data that's statistically significant, which we do in this case. Okay. Now, the second number here, the F statistic, okay, let me go over how to compute this. Okay, it's not too difficult once we have what we have. You'll notice that next to these sums of these various columns that I have another column here referring to the degree of freedom. Okay, now what do these degrees of freedom refer to? The number of degrees of freedom in our overall regression, okay, is related to the total number of data points that we have and the total number of coefficients, the total number of slope coefficients that we estimate in our model. Okay, so let's count the total number of observations that we have. I'm going to put a calculation in here for num_obs. I'm going to say this is equal to the count of column A. Okay, so we have 935 observations. Okay. Now, this number here, okay, the number of degrees of freedom for corresponding to the sum of squares total is simply 1 minus the number of observations. Okay. 1 minus the number of observations. And then notice here I have an average. I've computed an average, which is simply this number divided by the number of degrees of freedom. Okay. Now this number here actually, this number that we've just computed, if you trace back and see where this number comes from, you'll realize that this number that we've just computed is the variance of wage. Okay. Okay, number of degrees of freedom associated with the regression is equal to the number of slope coefficients that we estimated. And in this case, since we estimated one slope coefficient, the one associated with education, there was one independent variable here, education. Okay, so the number of degrees of freedom associated with the regression is equal to 1. The number of degrees of freedom associated with the error is equal to the number of degrees of freedom total minus the number of degrees of freedom in the regression. So in this case, it's 934 minus 1, 933. And so for each one of these sum of squares, I've divided that number by the corresponding degrees of freedom. I've basically taken an average. Okay? The F statistic is equal to the average for the regression divided by the average for the error. It's the quotient of these two numbers here. Okay? The p-value corresponding to that F statistic, okay, requires me to call the F distribution. So I call the F distribution, that's what this function fdist. The first argument in that function is this F statistic that we just computed. Okay? And then the last two arguments, notice it asks you for 2 degrees of freedom. Those are the 2 degrees of freedom that were used in computing the F statistic, this 1 and this 933, okay, corresponding to the fact that we divided here the sum of square residuals by the sum of square of the error. Okay, so that's where those numbers come from. I'm not going to go over in detail what they mean in this video, okay, or why exactly is it that the F statistic is always computed in this way and has the corresponding degrees of freedoms that it does. Okay, the explanation there is a little bit technical, but it suffices to know that the computer performs these calculations for you when you do the regression. Okay, so you can see here my numbers here are exactly the ones I've just computed. Okay, and that these numbers tell you about the statistical significance of the overall regression model. All right, thanks for watching, and I'll see you guys in class.